Thank you. So my topic is popular matchings. This work I'm going to talk about was carried out while I was visiting Kavitha in Mumbai. The outline of the talk, I will talk about stable marriages and popular matchings, and after defining them, I will show you how the Gay-Shapley algorithm works in both, and then I will point out the relationship between those two topics, and I plan to spend quite some time on open questions at the end. So the very basic stable matching instance is the following. We have a set of men and a set of women. They are all single and they know each other. Not everyone knows everyone, but they have relationships. And they have preferences.
You're just wondering about the air conditioning.
Oh, I have the control. Is it too cold or too warm?
Switch it off.
Switch it off.
We don't need it with so few people.
Good. So, so this is the graph. It's a bipartite graph. You have the preferences on the edges. During the entire talk, the preferences are built up the following way. The lower the number is, the better the edge is. So for the first man, the most preferred woman would be the second woman. The second best woman would be this lady, and the third one, this one, and he is not interested in being paired to the fourth one. We are searching for a matching which is optimal respectively to the preferences, which means there is no blocking edge. An edge blocks if it is not in the matching, and it is preferred by both of its endpoints to their partners. It's not very surprising. I guess all of you know that the seminal paper of Gale and Shapley from more than 50 years ago states that such a stable matching always exists in the graph. And also from the same paper, the Gale-Shapley algorithm, which I will return to later in this talk a couple of times, it runs as an old-fashioned propose-or-refuse procedure, meaning that all the men propose along the best edges, and then the women who get offers, they temporarily keep only the best offer and reject the rest. Now the single man in the second round propose again along the second best edges, and all the ladies consider the offers, including this lady who actually was engaged to a guy, but she got a better offer, which means she would just keep the better offer and reject the older partner. And this procedure terminates in OM time, of course, because every single edge is proposed along at most once. And this terminates with a stable matching. One more very important result that is known for quite some time is that the set of matched vertices is the same in all stable matchings, which also implies the result that the cardinality of the stable matchings is the same in one instance. It does not have to be a perfect matching or a maximum matching. It's always the same cardinality. And this theorem is also known as the rural hospitals theorem because of the very important application which actually came before the first result in '62 came in the theory. And that was the National Residency Matching Program in the US, where last year medical students had to be matched to residency positions in hospitals. We are talking about thousands of students. And there was a common scheme where actually some secretaries worked on these matchings by hand. And in the 50s, the demand was very large to automatize this procedure. And actually, those people who were organizing these matches, they came up with the Gay-Shapley algorithm without knowing that this is a Gay-Shapley algorithm, this is something mathematical. And what happened there was that they had more applicants than job openings. Yet the rural hospitals remained unfilled because no one wanted to apply to the rural hospitals. That's why this theorem is called the rural hospital theorem. I'll also return back to this later. So this applied view already gives you the idea that there is a huge demand for matchings that are optimal in some sense regarding the preferences, but that are also large as possible. And I think a very good notion for capturing both of these concepts is popular matchings. So what is a popular matching? We have the same instance, bipartite graphs, strict preferences on edges, and now we say, what could be the outcome of an algorithm? Well, it's a matching. So let's just take two matchings, the red one and the green one up there, and compare them. Well, the very intuitive way of comparing them, let's just ask the participants who likes which matching more. So they vote. Every single participant votes. The first man up there, for example, will vote red because his pair in the red matching is more beneficial for him than his partner in the green matching. This lady will vote green because she's unmatched in the red matching, so she would prefer the green matching, as you can see. This is the voting system, and then you count up the votes, and whichever matching gets more votes is said to be more popular. For example, on this, they are both equally popular. They get the equal number of votes. And I say that a matching is popular in an instance if there is no matching that could beat him, that could beat this matching in this voting system. Notice that I'm not claiming that the matching must beat every other matching strictly, must be strictly more popular than every other matching. This is not what I claim. I just do not want it to be beaten by some other matching. Is that clear so far? Very good. So this is also a very, very interesting paper from 75. Gerdenfort is actually a professor in cognitive science, and he publishes lots of stuff in non-mathematical fields. And he came up with this idea, and he also proved it mathematically that the popular matching always exists in two-sided markets. And then I think 25 years passed until another mathematician or another group of mathematicians actually found this concept and picked up the topic again. But this paper just went out in some behavioral science journal, and no one noticed it. This is a nice notion in mathematics as well. So this is the first result on connecting stable matchings and popular matchings, and this is quite strong, as you can see. I will also prove it. It's a very short proof. So it says that stable matchings are minimum-sized popular matchings.
Is the converse also true?
No, it's not true that all minimum-sized popular matchings are stable. It's not true. You will see examples for that. So the proof has two parts. First, I will show stable matchings are popular, and second, there is no popular matching that would be smaller. So stable matchings are popular. I won't need more than this room on the blackboard. This is a stable matching. How to show that this is popular? Well, what do I know about stable matchings? Well, not much more than the definition so far at this part of the talk. The definition is there is no blocking edge in this graph. So it means any other edge which is not in the matching is not strictly better for both end vertices, which means if I find another matching in this through an alternating path or cycle, then all these edges outside of my stable matching here cannot vote for the other matching. So one of these vertices has to vote for the stable matching. And this is true for the entire cycle or path, which means you can never get more votes for the other matching than for the stable matching. Good. So this was the part that stable matchings are popular. And then the other part, that there is no smaller popular matching. Now, let us assume that there is a popular matching. This is a popular matching, which is smaller than the stable matching, than any stable matching, because we know that all stable matchings have the same size since the rural hospitals theorem, right? Okay, so this is smaller. Then, if you take the symmetry difference with an arbitrary stable matching, then you will find a path, an alternating path, which is odd, which has more stable edges than popular matching edges. But then, let them vote. Okay, so this guy will definitely vote for the stable matching. Same here, because they are unmatched in the popular matching. And what about these pairs? Well, I had the stable matching as the dashed edges, which means either this one or that one, or both of them will vote for the stable matching, right? So at the end, you have more votes for the stable matching than for the popular matching, which then is not aligned with the popular matching definition. So, yes?
The Garden-Fonds proof, is it the same proof as the Fonds transaction proof?
That's a good question. I don't think so. I'm not sure, because I read the paper very long ago, and he does not have, it's not a math paper. It's a lot of economics in there. I would not say so, probably not exactly the same.
Yeah.
Yes?
But at the same time, prove that all stable matchings have the same size. Because if you apply if you have any two stable matchings,
Yeah.
one of them you can take as your
As a popular, yeah.
popular matching, and you prove
Yeah.
inequality.
Yeah.
It's a corollary.
Yes,
Yeah.
corollary of. Did you say it like that? No. You just mentioned that, but it follows from what you have.
Yeah, no, because I mean, if you have two stable matchings,
Yes.
you know they're unpopular matchings,
Yes.
and so they have to have the same size.
Yes.
So
This is what he says.
you don't even need to know the proof.
The fact. Yes.
You just need to.
There was one more question back there, yeah. No, you never compare all the matchings in a pool. You always compare two matchings in one round. So it is popular if it is at least as popular than any other matching compared to this. You cannot really compare them in a large pool and then count some global votes. For example, because this notion of popularity is not even transitive. I don't know whether you can see it. It's also a very simple sample instance. This is still a bipartite graph. It's just a four preference cycle. Now let's take this matching as one matching. This is M1. And then this one is M2. Now you can see that M1 is preferred by this one, but M2 is preferred by the other two. So M2 is more popular than M1. And then you go to M3, M4, and then M1 again. So you end up with a cycle. Now you could say, yeah, you just took one edge. It's not even a maximum matching. But if you add some dangling edges here as last edges, and then you complete the matchings so that they will get maximal, if not maximum, then you will run into the exact same cycle regarding popularity. So that's one of the reasons why you can't just take everything and then find the most popular. You always have to compare two at the same time. Okay. So this is the first relationship between popular and stable matchings. We will go much deeper in this later. Great, so we know that stable matchings are popular, so we can find popular matchings, and then this is not really the end of the story, because the motivation behind defining popular matchings was to find large popular matchings, right? Larger than stable matchings. And there comes the question, okay, so how to find maximum cardinality popular matchings amongst all popular matchings? And this is an algorithm from 2012. It runs the following way. It's actually a two-level Gay-Shapley algorithm, if you want to put it that way. First, you start with the Gay-Shapley output. So you just let Gay-Shapley run on the instance. On this sample instance, it's quite straightforward why this is the Gay-Shapley output. Well, this edge and that edge, they must be in the stable matching because they are first choices of both endpoints. And the rest, well, all that remains is taking it in the middle edge. So this is the man-optimal stable matching. This is the Gay-Shapley output. Now comes the trick. So we are stable, but we want larger cardinality and popularity. So we sort of have to involve the unmatched vertices. And we'll do it the following way. The unmatched man, after the run of the Gay-Shapley, will get a charm function. This means that all women, matched or not matched, they will find the unmatched man incredibly attractive. In practice, this guy was unmatched, so he becomes charming. And he proposes again along its first edge. He will start his preference list again from the beginning. And he proposes for the second time to this lady. And she will think, okay, he's persistent, he deserves more care. And therefore, she will abandon her good husband for this offer. So the second round proposals are always better than the first round proposals. Great. Now what's next? Because that guy got single now, the third guy. But, I mean, he goes along the preferences, the Gay-Shapley preference list. He hasn't gotten the term function yet, because this is still his first round Gay-Shapley. But he goes to the second choice, and this lady is actually happy to take this offer, and she will reject whatever she had. Now we have one more single man, and he's through his preference list once in the first round. So he's in the position to get the charm function and start proposing again along the same list from the top. And then she will reject the offer from the green edge and then accept this charming man. And then that single man, he will go to the second offer, still in the first round of his Gay-Shapley. And then there is one more guy left, he on the left. So he also gets this charm function and proposes. But if you get two offers from two charming men who are there in the second round, then you will just take the better one. Is this clear how this works? So it is not running the Gay-Shapley once and then promoting all the men and then running it again. It matters that every single man goes through the list at most twice. It matters in which round you are. Even if your neighbor is in the first round, you could be in the second round as a man. So the runtime of this algorithm is very easy to compute because every man goes through their preference list twice, so it's still an OM algorithm. It's still a linear time algorithm. And there is more in that paper, in that Soda paper from 2012. Actually, it's a nice procedure that, you just let the Gay-Shapley run more and more and more times, and then you get nicer matchings, right? In some sense, yes. You get larger matchings. It's very easy to see that you never get smaller matchings, because once the woman is assigned to someone, once she's engaged, she will never, ever get single again. She can abandon the husband for someone better or someone with a charm function, but she will never get single again. This means the cardinality of the matching can only increase. But you can also show that by running the Gay-Shapley more times than twice, you get less popular matchings, but larger. And depending on what is important in your system, in your residency matching system, or whatever you work with, you can decide yourself how many times you want to run the Gay-Shapley. What is more important, larger matching or the more popular matching? So I think it's a beautiful algorithm, it's simple, and it's very powerful. A result that is also to the structure of max-size popular matchings, it's very recent. This is the analogous version of the rural hospitals theorem from stable matchings. So if you take the set of maximum size popular matchings, they all match the same set of men and women in every single maximum size popular matching. And of course, they all match all the vertices that are matched in stable matchings as well. Good. So this is how much has been known about the relation between stable and popular matchings. And when I was visiting Kavitha, we thought that there is something more behind. It would be nice to have some nice structure on max-size popular matchings or popular matching that we have not discovered yet. And we started investigating actually this very instance. So I'm going to motivate the next notion of dominant matchings on that instance. What are the popular matchings on the instance? So the stable matching is certainly popular. Let's just start with that. The red matching is the stable matching, the only stable matching. This is popular. You can believe me that that one is also popular. For example, if you compare it to the only maximum cardinality matching and let the vertices vote, then you can see that there are more people voting for the green matching. So the matching by the vertical edges is smaller, but strictly more popular than the max size matching. What if I compare the other two ones? What if I compare the large matching, the cardinality 3 matching, and the stable matching? So the purple edge is in both. And let them vote. Well, then you see that this matching from the horizontal lines is smaller, but also just equally popular, which might give you the hint that if you have those two matchings and you have to pick, if they're equally popular, you might just go for the bigger one. It's just an intuition. It's not a proper math definition, because the proper math definition comes now. I see that a matching M dominates another matching M prime if it is strictly more popular. It gets strictly more votes than M prime in comparison, or they get the equal number of votes, but M is strictly larger than M prime. So if you compare those two matchings, the red one and the green one up, then you see that they are equally popular, but the red one dominates the green one. And our result, which has been submitted but hasn't been accepted yet, is that such dominant matchings exist in every single instance.
Maximum size popular matchings are not like this?
Not all of them, but you are right. So all dominant matchings have to be maximum size popular matchings. Because if they are not popular, then there is something strictly more popular. And if they're not maximum size, then there is an equally popular matching which is strictly larger. So this is a subset of maximum size popular matchings, but not the entire set. Any more questions at this point? Okay. And so how to show this? I'm not going to show the entire proof because it's a couple of pages of case distinctions. But the main idea comes from stable matchings. It has also been a long-standing question. So you have popular matchings. You have this beautiful rural hospitals theorem on popular matchings. Can't you just create an instance where all popular matchings translate into a stable matching on some modified instance? Can't you just use some sort of bijection? Can you modify the instance? So this was also an original goal which we have not reached, but we actually got quite close to it. If you have an instance like this is just the previous instance without the dangling edges up there. Then you blew up the men this way. So women, B and B prime, they are just copied. And instead of every single man, instead of A here, there is A1 and A0 being introduced, and the dummy woman. And the same triangle here, or cherry then here. And then every single neighbor of A will get an edge from A1, and also an edge from A0. And we can show that every single dominant matching there translates into at least one stable matching here, possibly more than one. So it's not a one-to-one corresponding relationship. And every single stable matching here corresponds to a dominant matching there. As I already said, I'm not going to show this because it's very technical. But if you remember the two-level Gay-Shapley algorithm, this was also particularly copying the man. Like, there was a non-charmant man and there was a charmant man, and they were adjacent to every single woman. The original man was adjacent. This is not much different from that. And by activating the first man, or activating the charming version of the same man, you actually don't do much different than introducing this dummy woman, and in the first round, just matching her to her first choice, and then if she is rejected, then matching her to her second choice. So it is not very hard to see that the Gay-Shapley algorithm on this actually delivers the same matching that is delivered on that by the two-level Gay-Shapley algorithm. The rest, that the entire lattice of stable matching here translates into the entire set of dominant matchings, that's what requires a bit more effort and cases. But I hope you got the idea how those two instances are created, and it's not just magic. I introduced vertices. It actually is related to the algorithm we already had. So what is it good for? Because it's nice that we have now dominant matchings, and we have some relationship to stable matchings, and it's a structural result, but it's not only a structural result, it's more behind. They are good for a bunch of things. For example, why we wanted the stable matching so much? Because stable matchings have 50 years of literature. They have loads of results, and if we could just translate them to popular matching, that would be awesome, of course. We could not translate them to popular matching, but we could translate them to dominant matchings. You can even optimize over weight functions on stable matchings. They have a very rich lattice structure. This all holds for dominant matchings now due to this transformation. And there is the popular edge problem, which asks whether if I'm given an edge, is there a popular matching that contains this edge? This has also been a very crucial point in stable matching literature, the stable edge problem. Now we can solve this problem. It's also not straightforward how, but one can show that if there is a popular matching containing that edge, then there is also a stable matching containing that edge, or if not, then there is a dominant matching containing that edge. And those two are easy to check, because the stable edge problem is very, very simple to solve. And they both actually translate into a stable edge problem. And then one more question. So assume that the size of the stable and popular and max size popular matchings are all the same. We can't really distinguish between them how to find a popular matching that is not stable, how to find a popular matching that is not dominant. It's all the same cardinality. And by defining dominant matchings, we can answer the question whether there is an unstable popular matching in the instance, or all popular matchings are stable, which was also asked at the very beginning of this talk, I think. So these are all questions that could be answered with the help of dominant matchings. And so I also have a bunch of open problems I want to talk about in a bit more details. First of all, so I told you that we can, using dominant matchings, we can decide whether there is an unstable but popular matching. Now, analogously, you could ask the question, is there a popular matching that is not dominant? We don't know, because we have two different algorithms for computing a maximum size popular matching, but they always produce dominant matchings. So somehow dominant matchings are easy to find. And we don't know whether there is any algorithm to decide this. And then I also showed you this popular matching problem, or the popular edge problem. But so if I'm given A, B, and C, D, I can decide whether there is a popular matching containing A, B. I can decide whether there is a popular matching containing C, D. But is there a popular matching containing both of them at the same time? We don't know. I can very well imagine that this problem already becomes NP complete. And actually, we tried to exploit the results we had with the one edge case, and they just somehow, they get stuck at the one edge case. And then this has been a very long-standing problem, and I think the second question sort of leads towards this third one. Is there a popular matching of size exactly T? We also don't know this. Oh, I don't think we have to draw. So if you take this instance, what's up here, it's sort of harder to see, but there are two sizes of popular matchings possible, 4 and 2. There is nothing of size 3. Well, there's nothing of size 3, you can see that because I showed you how they dominate each other, how they are more popular than the other one in cycle. So if you take only the coordinated 3 ones, then they will be just more popular than the other one. On the other hand, if you take a stable matching, or if you take the large matching, they both will be popular. And you can extend this example actually to any size, where there is a popular matching of size n, there is a popular matching of size 2n, and nothing in between. So we don't know how to answer that question. And we also talked about algorithms that actually could take a matching and make it popular by augmentations. Now, such results, such examples show us that it's probably not a feasible option to do so, because there might be a huge gap between the sizes of popular matchings. And then the last question. This is probably the biggest open question of the field. Is there a popular matching in a non-bipartite case? So I only talked about bipartite instances so far, but why would you stick to bipartite instances? Stable matchings are defined very easily and exactly the same way as on non-bipartite instances and as on bipartite instances. And it's easy to decide whether there's a stable matching in non-bipartite instances. And if there is none, there comes a problem, because if you have a non-bipartite instance which has a stable matching, if you remember the proof why stable matchings are popular, you actually did not need the bipartite property of the graph. That proof carries over. So even in non-bipartite graphs, stable matchings are popular. The problem is there are instances, non-bipartite instances, where there is no stable matching that exists. The easiest one is this preference cycle. So the only matching you could take would be one edge. But then you will find a more popular matching, right? Because this is unmatched and this vertex is happy to switch. And then you just go around. And all the three matchings that come into the question, they are dominant. They are less popular than another matching. So in this instance, there is no stable matching, and there is also no popular matching. On the other hand, if you just modify it a tiny bit, by introducing one more vertex here, which no one likes in the cycle, then in this instance, there is no stable matching, but there is a popular matching. So this matching will not be stable because this edge blocks, but it will be popular. It's quite easy to check, but it will be. It is not outvoted by any other matching. So the question is how to identify those instances that have no stable matching, but they have a popular matching. Yes? Yes, and this is very simple. They don't have any odd party. An odd party is an odd preference cycle like this, of any size, but it must be 1, 2, 1. I mean, not 1, 2, but like it must be this preference relation in the same direction on every single edge. And they also always admit a half matching, a stable half matching. And we could not come to any conclusion saying that there is a dominant or there is a popular half matching. So that does not carry over. There would already be a result. But there's almost nothing known about the non-bipartite case. There is one single paper on that which says things about unpopularity factors. This means the ratio of agents that prefer M to M prime. So one unpopularity matching is a popular matching. So it is some sort of approximation in terms of popularity. But there is nothing else known about the non-bipartite case. Any more questions? Because if not, that was it. And thank you very much for your attention. Yes?
You mentioned the algorithm that and you told the algorithm that maximizes popular matching. Is there a min-max theorem, a Curry's theorem for maximum size popular matching?
You mean? How do you mean a min-max theorem?
Well, the obstacle. What is the obstacle for having an even bigger popular matching?
Oh.
Curry's theorem.
Oh, okay. I'm not aware of anything like that. You have a characterization using augmenting paths, but I could not say anything like max flow min cut.
No.
I'm not aware of anything like that.
Well, the weighted case, the convex halo, and the convex.
Mm-hmm.
So that's not known, the convex halo popular matching.
I don't. Is there any LP? I mean, is there any very straightforward? There is an LP. There, of course, for stable matchings, yeah, that's very solid, yeah. Yes. Yes. But for popular matchings, no. I also don't see any relation why it couldn't be characterized as just a polytope. Anything else?
So the stable matching is one, but not only like the non-matched.
I don't think there is one for non-bipartite. There is one for the many-to-many case. And I think it stops at the stable allocation case where you have capacities and quotas on edges. This is where we don't have a description yet. So it was generalized into that direction of the capacitated direction, and that works.
I recently saw some papers where they considered stable matching with ties,
Oh, yeah.
where some people are indifferent.
Yeah, so actually popular matching started when popular matchings were picked up for the second time after Gerdenfoss around 2000. Then they considered the one-sided case, not the two-sided case, which means that you still have a bipartite graph, but only one side votes. And this is a completely different setting, and with completely different complexity results. It's very easy to show that you have instances where there is no popular matching. So they vote, how do you have, okay, this is just this. They vote, they don't vote. There is a tie, a big tie, they don't care. And then they have the same preferences. Then whatever matching you take, there will be a more popular matching here, because only these one vote, and they don't. So there is this case, which is the one-sided case, with absolutely different complexity results, but it's also well studied. And there is one more case, which is closer to the stable matching case with ties, where both sides vote, but they can have ties. Now that also have some complexity results studied. If the case is that one side always has a huge tie, nothing else. If you imagine that, I don't know, there are some museum rooms that have to be guarded by guards, then the rooms only care about being guarded, but the guards care about which room they get into. So they have strict lists, or strict lists with ties, and they only have one big tie. Then the problem becomes polynomially solvable. There is an UN square time algorithm if it's strict and one tie. So one side is strict, one side is one tie. On the other hand, if you have strict, and this is either one tie or strict, so it's only those cases are allowed, then this is already NP complete, this case. So there is much literature on ties, but in general, the popular matching with ties is NP complete, even in this quite special case. Yes? Yes, yes. This is very new. I think Jianchun Huang and Naoki Kamisama, I think, is working on that. And there is not much known. So it is a very straightforward thing that some people have vote of weight 2. They always vote for one possibility, but that is a weighted one. So. Oh, you mean it's not ordinal but cardinal preferences? I'm not aware of literature on ordinal preferences, or on cardinal preferences, I'm sorry. But that also might be, the only thing I'm aware of, and this is also work in progress, is that a vertex has weight, and it votes with, I don't know, it has a big family, and then it votes with as many votes as the family members are, and that also, even in the two-sided model, where stable matchings are just popular and end of the story, even in that case, if you allow weights on the vertices, then there might be instances where there is no popular matching. So that also changes radically the complexity.
Isn't the variant that you described equivalent to simple normal weighted matching?
I don't think so.
Transfer the weights to the edges?
Not exactly, I don't think so. Because you still compare votes. But, so it's, so if you have one person, and then if you compare, I don't know, those two matchings, then it will say it's, I don't know, it's half better. But if you compare those two, then it will say it's, I don't know, it's 10 times better. And I'm not even sure, I mean, how do you, why would you assume that this is transitive or additive or anything like that? So it does not have to be additive, for example, and then there is no way you can translate it into a weighted matching. But it also, of course, depends on how you define this cardinal vote function, and I think this is an offline discussion. Okay, good, thank you.